In this video we're going to take a look at the name server challenge in the Tamil CTF. It's a pwn challenge. It's actually the easiest pwn challenge in the CTF, but we can demonstrate a classic return to Lib-C attack here. And I've got quite a few new subscribers over the past month or two who might not have seen some of my older pwn videos, so I thought this would be a good challenge just to walk through the steps for anybody who's not too familiar with binary exploitation. So we've got the server to connect to, which we need to basically exploit a buffer overflow to get a shell and retrieve the flag. We've got a file to download here to take a look at it locally first of all, so we'll try and get a local exploit working or develop the exploit locally, and then we'll test it out against the remote server. So you can see I've already got this downloaded, and we can have a look at the file type here. It's a 64-bit LSB executable. It's not stripped, which means if we're trying to reverse engineer this, we'll be able to see the names of functions and things like that, which make it a little bit easier to read. We can run Checksec to find out what protections are enabled on the binary. So we can see here that pi isn't enabled. We would have seen this here as well in the file information, but this just means that each time the program loads, it's going to load at the same base address. So if this was enabled, then we might need to worry about leaking out some address and then calculating the offset to the base of the binary. Not too important here because you don't need to worry about it anyway. So the NX enabled means we're not going to be injecting shellcode onto the stack because it'll be marked as not executable and won't execute. So we're likely going to need to do some kind of ROP chaining using ROP gadgets. And there are no stack canaries. If there were stack canaries there and we tripped a stack canary, so if we overflow the buffer and overwrite the canary with a value that it didn't start off with, then it'll basically crash out the program, say stack smashing detected or something like that. And then partial railroad, again, don't need to worry about it for this challenge type, but this just refers to the writability of the global offset table. In some challenges we might be trying to overwrite elements of the global offset table. Again, I'm not going into all of that. Let's go ahead and open this up first of all. Let's try and run the program first of all and just see what actually happens. If we try and run it, it asks us for a name. Let's try and put in a name, which, I mean, we have no idea what size the buffer overflow is here, but just try and put in quite a few characters, and we get a segmentation fault, so the program did crash. So what we want to go and do is try and find out how many A's do we need to input here before the program crashes, because what's happening when it's crashing there is it's trying to load some of these A's as a memory address, which will be like 41414141 in hex, which isn't a valid memory address, which is causing segmentation fault. So we can open up GDB. I use the PwnDbg plugin, but you can use Pedder or Jeff or something like that. We can open that up with nameserve, and we can have a look at the functions in here. Oops. We can have a look at the functions in here. We can disassemble functions if we need to. So in terms of getting some gadgets or some function addresses. So for example here we can see the main is 400607, and every time the program loads that's going to be the same, but if pi was enabled, then the offset would remain the same, so it would still be like 607 every time, but the actual base address would change, meaning when it comes to using the server and stuff we'd need to leak that. And you can actually, in GDB you can use pi base to calculate what the base of the binary is, and you can use break RVA, which will allow you to set a breakpoint at whatever offset you choose from the pi base. I cover quite a lot of this in some of my old pwn videos where I've gone through hack the box challenges and stuff, so if you're interested you can check that out. But for now, let's generate a cyclic pattern. We'll say cyclic 1000. I'm going to run this program again, but instead of sending in all those A's, we'll send in this cyclic pattern. And now we'll be able to go and try and find out whereabouts in the block of text are we overwriting the return address. So in this case we're looking at the RSP, the stack pointer, and it's basically these first 4 bytes here, so the KAAA, KAAA, these would have made it into the return address here. You can see they would have executed, but obviously it's an invalid memory address. But we can basically have a look now with the cyclic command that we use to generate that cyclic pattern. We can use cyclic-L to look up the offset of that and find out that it's 40 bytes in. So if we write 40 bytes, we'll then be able to overwrite the return address, which will redirect the execution of the program to whatever address we put in there. So if we were to go here and say, let me do Python 2, we'll do Python 2 and we'll print a times 40 plus b times 6, and let's just print that out. Let's try and run the program again. Asks for the name. Let's paste that in just so we can visualize this. You can see that we've got a lot of A's showing up here right up until we get to the RIP, where you can actually see we've got these B's in there, the RSP. So what we're going to want to do is go and put together a script in PwnTools, but first let's have a look at the actual code of the program. Again, we could have a look at the disassembly code here and the functions, but I've got this opened up in Ghidra as well, so let's take a look at it there. So we jump over to Ghidra. We've got our decompiler on the right for our decompiled code. We've got our assembly code here, and then we can see our functions or imports or exports and things here, and then different sections of the program up here as well, like the global offset table. So if we have a look at the main function here, there's not really too much going on in the program. So we've got a buffer of 32 bytes at the beginning. We have, it asks us for a name, which we see whenever we run the program, and then it's going to read in 500 bytes into this 32 byte buffer. So you saw that our offset was at 40. You could pretty much calculate that by just going and having a look at the disassembled code here. But the issue is, what we're going to do if we overwrite the return address here so that it returns somewhere of our choosing. We don't have any functions here which are just going to print out the flag. If we had a function called win, we might just overwrite the return address with the address of that function, and then that function would give us a flag. But in this case we don't have that, so what we need to do is try and return to the Lib-C library. So if we go back to our global offset table here, we can see we've got puts, we've got printf, we've got read, and these are functions which are called here in the main function. And basically, because each whenever you load the program on your operating system, it will call out to your Lib-C library. So each system you run might have a different version of Lib-C, and the offsets of these functions will be in different places. So what this section of the program's essentially for is to populate the global offset table with the addresses of those functions in Lib-C. So the program will load, and the first time that it calls puts, it'll basically make a call out to Lib-C and find out what's the address, what's the offset of this in the Lib-C library, and then it'll populate this global offset table so that it doesn't have to keep making that call out again. So if we can wait until puts is called, or if we can call it and leak out the address of puts in the global offset table, we can then try and find out what are the offsets to the other functions. So for example, system and the string bin sh, and then if we can call system bin sh, we've got a shell. So our goal is going to be, first of all, to leak an address from the Lib-C, from global offset table, which is going to give us a foothold into the Lib-C library. And then we want to use those addresses to send another payload, and the second payload is actually going to get us a shell. So I hope that's explained that okay. Let's go and try and put together a script to do this for us. Now, with these kind of exploits, you quite often find that code can be reused. So if I'm going to do a return to win or return to Lib-C or any kind of format string vulnerability exploit, I'll normally go and have a look at some previous scripts that I've used on GitHub, and quite often you'll find that they're quite reusable. So for example here, I'm going to go and grab one called ROP, and if we have a look at the code, we should just be able to edit a good bit of this. Let's call this exploit.py. We can paste this in here, and let's take a look at the code. So first of all this stuff basically stays the same every Pwn script that I write. We've got a function here to call a start function, which basically means whenever we run the program, we can either run it with debug in capital letters, and it will run our GDB script, so we can go and start having a look through the code, setting up breakpoints and things like that. Or we can run it with remote and a server and a port number, and it'll run the exploit on the remote server, or we can just run it locally. So We also have a function here to find the instruction pointer. In this case, I've found that the instruction pointer was equal to 40. We did that in GDB, so I'm just going to set that there instead. And then here's just where we set up our file. So we've got our file is called name.serve, name-serve, and this is going to set the context for the binary. So whenever we're writing our exploit here, we don't need to worry about making sure that this is in the right format, i.e. the 64-bit, because it's going to look at our binary here and find out, is it 64-bit, is it for Linux or is it Windows, is it little endian, and then whenever we use flat or whenever we use pack, it'll take care of all the context for us. So we don't need to do like P32 or P64 unless we specifically want to pack it to that size, because it'll take care of that for us. We can just do pack. Similarly, if we're doing some shellcode, if we're doing like shellcraft, we can, instead of saying like shellcraft.linux.x64.cat flag.txt, we can just say shellcraft.cat, and it'll know that we're dealing with Linux, it knows that we're dealing with 64-bit, so it'll do all the rest for us. And then this is where we're going to do our exploit. So you can see that this is kind of the generic exploit I was talking about setting up, where first we're going to leak a Lib-C function. So in this case, we set up our first payload and say that we want to pop the global offset table, the puts address in a global offset table, into the RDI register, and then we want to call puts, which will put out that global offset table address. It'll leak the address, and then we want to go back to the main function again so that we can do our second payload. So if we go back to Ghidra and have a look here at puts, and you can see here it says that the char pointer is in the RDI. So we know that whenever we're setting up this exploit, we want to make sure that whatever we want to put out to the screen, we first need to put it into that RDI register as a parameter. So that's how this is put together, and what I'm going to do is just comment out most of this code just so we can go through and test this. I just want to show, because it's a completely different challenge, but I just want to show how reusable some of this stuff can be. Let me take this out. We need to know what we're sending the payload after, so if we run name-serve, you can see it's sending it after a colon, so I'm going to change that. We also need to find out where is the pop RDI gadget, so we can use wropper to do that. We can do wropper -- file and pass in name-serve, and then we'll search for pop RDI. You can see we've got a gadget here. It's actually the same location, great. And we're flattening our payload here, so we're basically saying at this offset we want to inject this list of addresses. So we've got a pop RDI gadget, our puts, and then main. It's going to inject it at 40, and we want to send that off, and then we want to see does that leak out the payload. So this will come back in a form where we're able to extract it and unpack it into a number. So let's test it out first of all. We try and run that, and you can see that it's come back with our address. It hasn't given us that nice leak that we want to see. We were trying to unpack it here, so what I normally do is just let's try something else, receive line instead of receive. It'll just vary from exploit to exploit, and you can see that that has come back, but we've actually got a 2.0 at the end there, so we've got a space at the end. So what we'll also do is say receive line dot strip to strip out any spaces of stuff at the end. We run that again, and that's looking a lot better. And because what I mentioned about the template that we're using, we can also just now say we want to run this with GDB, and we run it with GDB. It pops open another window. I've actually set a breakpoint at main. You saw that in the script up here, so you can take that out if you want to. So we'll hit continue, just continue towards the end. It leaks out this, let me just make it so you can see it a little better. It leaks out this puts address, and what we're going to do here is say x that address, and just make sure this lines up with puts, and it does. And we could do the same thing. We could say x system and find out where is the system address in Lib-C, because that's what we're going to want to find. And we could also then say, okay, well, we want you to print out what is the offset between these two functions. There's a way to do it passing in the function name, but I always forget how to do it. So that's the offset in decimal, and we could do that again, p/x if we want to print it as hex. And we could just go and update our script now then to calculate the offset to system. What I generally find is better to do is find out what the offset to the base of the binary is first, the base of Lib-C, and then you can calculate all the different functions from there. Okay, so let's close this down. Let's jump back over to the script. And basically from here then we want to set up our next payload. Our next payload is going to be the bin.sh, and we can find out what is the offset between puts and Lib-C. So let's actually, we can do this in a lot of different ways. What I normally do here, if we do ldd nameserve, and then we find out this is the Lib-C library I'm using, so I can say readelf-s and then paste that in. This will give us all the offsets to the different Lib-C functions, and we can just grep out what we're looking for. So in this case I'm looking for puts. You can see we've got our puts right here, and we can take this offset and basically say I want to subtract this, and it's the same offset there, so I'm still using the same Lib-C library as whenever I did the Hack the Box challenge locally. And we've now got our base address for Lib-C, which means we can now say if we want to find out where system is, we can do the same thing again. Say whereabouts is the offset system, it's 4AE5, so we can just go back to our code, we can add that in here and say our system address is at the Lib-C base that we just calculated plus this offset to system. And we can do the same thing with bin.sh. What we need to do there is do something like strings, and we'll do -tx to represent it in hex, and then pass in the Lib-C library, and then we want to grep out /bin/sh, and that will show us the offset of bin.sh. So we can just go and insert that as well. As you can see, this is the same each time because I'm still using the same Lib-C library. And then we would just go ahead and uncomment our second payload. So just to cover again what's happening here briefly, we're leaking the address of the puts function in the Lib-C library, and then we're calculating the offset to the functions we need to get a shell, like system and the bin.sh string, and then we're creating another payload here where we're going to basically pop the bin.sh string into the RDI register ready to call system. And then we go ahead, we're going to send off that payload again. We want to do it the same as we did here because we've gone back to the main function. We could go back to a different address as well and basically skip out that prompt probably, but we can go ahead and try that. Let's try and run Python exploit. You can see it runs. I actually get an end of file here, which I was getting whenever I was testing this as well. Let's try and grab, sometimes you need to make sure the stack's aligned, and this quite often happens whenever I'm testing exploits locally. They work, which it's not in this case, but typically they work, and then whenever I try it against the server it doesn't work, and I have to sort out the stack alignment. So you can add like a ret gadget in here. Let's put this up with our pop RDI, and we can insert the ret here. Let's see if this makes any difference. I actually don't think it will. Try and run it again. It doesn't. I'm not too sure what that error is about. No, if anybody knows, let me know. So what I did here in terms of getting this working though was just to try and test this out against the server, because even if we did get this working locally, we'd have to go and find out what version of Lib-C the server is using, because it's going to be completely different offsets to all the functions here. So if we go and grab the server address, we can copy the server and the port number here, and because we're using that template, we can just paste this in here with remote in capital letters, and that allows us to very easily swap between locally and remotely testing. You can see we've leaked out this address here, the got puts, and the best thing to do here, I find, is just go to the Lib-C database, which you can see up here is libc.bluecat.me, and we can basically say in here this is the address that we've just grabbed of puts. So we can just say in here that this is the puts address, and we go to find, and this will find all of the potential Lib-C libraries based on that offset. If you're able to find a couple of different offsets, then you could enter multiple ones in here, and that will narrow down the potential. I think it was the 9.2 for me. I think this is the one that I tested. Obviously we're looking, you can base the architecture and stuff on what's going to be more likely, but this will basically tell us then, let me zoom in a little, this will basically tell us the addresses of all the important functions. We can go and have a look at them all here as well, and we can download the Lib-C library. So I'll show what we could do with by downloading that as well towards the end. But if we wanted to test these out, basically we'll go and update these. So we know that puts in this Lib-C library is this. We can have a look at the difference, or we can use offset. I'm going to use the offset, and I'm going to go and just update this offset right here for the puts. And then we want the offset of system as well, so we'll go and update our system offset. And we finally want the offset of bin.sh. So let's go and update that as well. And that's all of our addresses updated. So we basically just need to test this out and see, does it work against the remote server. And if we run that, you'll see we got no end of file, which is a good sign. If we do ls, we can see we've got the flag, we can run whoami, and then we can also cat out our flag.txt. And that's the challenge solved, but let's see what else we can do with PwnTools. So you saw that the process there of updating these offsets was quite manual, and if we wanted to do that with all of these different libraries, that would take quite a long time. So one thing that we could do is download all of the potential libraries and then kind of script it so that we can just loop through the different potentials. I'm just going to download this one first of all, just so we can test this out a little bit, and I'll kind of show you what I mean. Let's move this from downloads here, and I'm going to take the name of that, and let's go and update our script here a little bit. So in our script we can actually add the Lib-C library. We could say lib-c is equal to, and we'll create an elf file. We'll pass in the address of that. So this is the one that this is the Lib-C that the remote server is using. We could also do this with our local. So we could say that our local is ldd nameserve. We take a copy of this, and this just means that we could basically go and comment out whichever one we need to, depending whether we're testing local or remote. So this was the remote, this is local, and we can also, once we leak the address of Lib-C, we can update the offset of it and just start using this actual binary here instead. So rather than creating this variable called Lib-C base, what I'm going to do is this binary that we've created, Lib-C, I'm going to say Lib-C, and we'll say Lib-C dot address is equal to got puts, and instead of this offset here we'll say minus Lib-C dot symbols dot puts. And this means we've now got our Lib-C base. It's actually the Lib-C address instead, and we don't really need, we could take this out as well if we wanted to remove a bit of code, but that means that when we get down here we can just say that we don't need this address at all. We can just say our system is libc.system, and we could look for the bin.sh address as well. So instead of this bin.sh, let's say it's next. So we're looking for the next value in the libc.search, and we'll search for the string bin.sh, and we could put a null byte there just to make sure we don't have any issues. That might have actually been causing issues for me previously. Let's have a look and see. I guess it won't. So we can take out that bin.sh as well. Let's test this out locally, although we didn't have it working locally before anyway. Elf object. Okay, we tried to call libc.system instead. We need to call libc.symbols.system. Let's try that again. Switch into interactive mode. Okay, so we actually got a shell. So locally we weren't getting a shell before, and we did this time. Maybe it was something to do with the null byte there. So we've got this working locally. Now let's see if we just change this Lib-C library over to the one that we downloaded. Obviously if we run it locally we shouldn't expect it to work because it's got all the wrong offsets, so we don't have a shell. But if we try this remotely again, and you can see that we have a shell. So now we can just very easily swap between the two Lib-C libraries, and if we didn't know what version of Lib-C to use, we could download all of the potential Lib-C libraries based on the address that was leaked, and we could just have a for loop looping through until one of them gets a shell. So I hope that helps in terms of automating some PwnTools stuff a little bit. Let me just show some final tricks that we can use to automate ROP objects a little bit more. So if we really want to step this up a bit, what we can do, we can take this out altogether. Let's go back to our local first of all. I'm going to take out the ROP gadgets because we don't need them anymore, and instead of this payload, what we're going to do is we're going to create a ROP object. We'll call it ROP, and then we'll do ROP elf, and this is basically taking in this elf file, our name serve, and it's going to automate a lot of the process for us. So we want to leak out the puts address here. All we need to do is say ROP.puts, and then what do we want to leak out? We want to leak out the global offset table puts address. And then what do we want to do next? We want to go back to main, so let's just say ROP.main. And we can go ahead then, and if we want to print some of this out, we can do pretty print and then do ROP.dump, and this will basically show us a ROP chain that it's compiling here. And if we want to send this off, let's, instead of doing this payload, let's actually just say that we want to send our flats, and we'll do ROP.chain. And you can see here that ROP.chain will build a ROP chain containing the raw bytes, and now we can just take out this entire payload. Sorry, no we can't. We need to make sure we send this off at the correct offset though, so let me actually let me take all of this. Let's put that in there, and let's say at the offset we want to just send ROP.chain. There we go. You could put that all onto one line as well if you want to make it a bit neater. And this is doing the exact same thing that we did here. It's doing that all in one line. And then we go ahead, we leak our address just as we did previously. We update our Lib-C, and in fact what we can do here as well is go and update our ROP object. So we can say now that the ROP object is equal to ROP Lib-C, because now we want to do the system. And just like we did up here, we can say ROP.system, and what do we want to pass in? We want to pass in this bin.sh string, and that should be good. Let's just do the exact same thing here. Instead of that payload here, let's get rid of this entire payload, and let's do the let's print the ROP.dumpers again just so we can see what's going on. Tidy this up a little bit. And if we run this locally, it's trying to load the gadgets. Let's have a look and see what it's done here. So we dumped out using pretty print, we dumped this out, and you can see that it's built a ROP chain, and it's basically gone and found pop RDI. It's put into the RDI register the got puts address, then it's called puts and put that out to the screen, and then it's called main. So everything that we did is done automatically. And then it gets to the second ROP chain, and because we've updated it to the Lib-C library, it calls pop RDI, and then in the RDI it puts the address of bin.sh, and then it calls system. So if we do ls and who am I, we can see that we've got our shell, and because all of this is set up so that we can just go and update this Lib-C library now, we just set this to the remote server again, run the program, and this time we actually get an end of file. Okay, I'm not sure what caused that. Okay, well normally that will work anyway. I can't really be bothered debugging this now. We've already solved the challenge multiple ways. But yeah, I hope you enjoyed this video. If you're interested in learning more about binary exploitation, check out the ROP Emporium challenges. I did a video series on them about 9 months ago, and although the quality of the videos is probably pretty poor compared to the videos I release now, hopefully, I think technically they were probably some of my best videos. Yeah, any questions, comments, leave them down below. Thanks.